Hey everyone, tonight we're going to drift a little farther, not into the forest, nor into a dungeon, but outward, beyond the sky, beyond even time itself. We're stepping into the very beginning of everything. Not a fairy tale, not science fiction, but reality. Forget the colorful pictures of stars you see on Instagram. The truth is, we still don't fully understand what really happened. We're just tiny creatures, trying to piece together fragments of the universe's memory. A universe that, at its very first moment, was smaller than an atom. Now, turn off the lights. Put your phone down, close your eyes if you want, and let your mind slowly drift to the very first moment, the moment when nothing became everything. The sky is a vast ocean of mystery that humanity may never fully explore. Since ancient times, people have likened the stars to gods, supernatural beings with immense power, capable of ruling over mankind. But those were only myths, not truth. Ever since science rose and pulled humanity out of the Dark Ages, we've tried to separate myth from reality, focusing instead on explaining the universe through the laws we've discovered. And yet, as science progressed, the old stories of gods began to feel strangely real. Could it be that everything is pointing to the same place? That somewhere out there, a supreme being really did design it all? When we talk about geniuses, we immediately think of names like Newton, Einstein, or even Tesla. But no matter how brilliant they were still human, and humans are flawed. During his years of studying and exploring the universe, Einstein made groundbreaking predictions that pushed mankind forward in the journey of cosmic discovery. However, alongside his achievements came mistakes. Mistakes that Einstein himself admitted were the biggest blunder of his life. To talk about that blunder, we need to go back to a time when Einstein wasn't yet the world's most renowned scientist. This was the time when his theory of relativity had just been published, and the scientific community did what it does best. It refused to accept it. The essence of science lies in tests and experiments to verify claims. Instead of trying to prove something is right, science tries everything to prove it wrong. And when it can no longer be proven wrong, then it must be right. This frustratingly rigorous process is exactly what separates science from pseudoscience. Because real science must follow laws and established principles, it must never be explained by mere coincidences. So when Einstein proposed the theory of relativity, a theory that had the potential to dismantle centuries of Newtonian science, the scientific world was incredibly strict and tried to test it in every way imaginable. And then, through each calculation and experiment, Einstein's theory of relativity gradually emerged as the victor against Newton's laws. One of Einstein's greatest triumphs came when scientists applied Newton's laws of motion to Mercury. According to Newton, an object moving in a vacuum without any external force should not change its speed or direction. Mercury travels through a vacuum orbiting the Sun, meaning its orbit should remain unchanged. But strangely, Mercury's orbit does shift over time. Meanwhile, Einstein's theory of relativity proposed that space and time are one and the same, and together they form a stage upon which matter performs. Essentially, the Sun is a massive object that warps space-time, causing other masses, specifically planets, to fall into its well. And like any object caught in a whirlpool, their orbits cannot stay fixed. From that, we can explain the subtle orbit of Mercury, and even the paths of any other celestial body in the sky, something Newton's laws struggled to carry. To put it simply, Newton's laws can describe the motion of matter in the universe quite accurately, but Einstein's theory explains the root cause of that motion, and from there we can use it to predict the movement of matter in a vacuum. Einstein's theory of relativity didn't reject Newton. More precisely, it completed his work. Over time, scientists began to accept relativity and considered it the foundation of astronomy, of cosmology, and something that could be applied across many other fields of research. But this is where problems began to arise. If Einstein's theory of relativity was the perfect model for the universe, If matter bends space-time and that curvature causes gravity, then shouldn't the universe collapse in on itself? More specifically, if gravity is the only force at play, shouldn't the universe be shrinking? Why isn't it? This universe began over 13 billion years ago, and if gravity ruled all, then those 13 billion years should have pulled everything together into one massive lump. Instead of galaxies, stars, and magnificent nebulae, the universe would be one gigantic silent black hole, devoid of life. And yet, here we are. The stars are still out there, the nebulae still scatter across the sky. So, does that mean Einstein was wrong? To deal with this problem, Einstein introduced a concept called the cosmological constant. A counterforce to gravity, it's written in his equations as the symbol L, lambda, and acts as a force that opposes gravitational pull. It represents the idea that something exists to push matter away from its original location, an opposite force to gravity, that keeps the universe in a static state. Sounds grand, but in truth, the existence of this constant felt like Einstein was making something up just to cover a flaw in his theory. Why should there be a force that counteracts gravity? The existence of this constant sparked a new debate about the laws of the universe. That maybe, like relativity or Newton's laws of motion, it's still not complete. Or maybe, in all our brilliant calculations and predictions, we've overlooked the most important thing, that we are only human, and the universe is far too vast to be reduced to a few simple laws. Maybe Einstein was right, that some hidden force is preventing all matter from collapsing into one. But maybe he was wrong, and this world is simply too big for his equations. And no matter what the truth is, science is still science. Its greatest mission remains: experiment, question, seek answers. So now, the next question is, if the universe isn't static, like Einstein assumed, then what is it really like? Einstein's theory of relativity accidentally assumed that the universe is static, that matter simply drifts endlessly around each other, unchanged forever. And to ensure that gravity wouldn't ruin this perfect picture, Einstein invented the cosmological constant to balance it out. However, this wasn't the first or last time someone assumed the universe was static and tried to explain it in a detailed way. Long before Einstein published his theory of relativity, many scientists had already looked up at the sky and questioned the stillness of space. Why must everything be still? It's such a simple question that it makes us wonder why we didn't question it sooner. Could it be that we've all deluded ourselves into thinking the universe must be perfect because it's supposedly the creation of God, that everything must stay in a state of balance just to satisfy our own intellect? But reality always lies far beyond imagination. Since the genius mind of William Herschel, a German composer and astronomer, discovered infrared radiation in 1800, the world has never been the same. Other great minds built upon the concept of infrared rays to explore the entire spectrum of light, from the visible to the invisible. Light, like other waves, has a frequency, and this frequency determines its color. The visible spectrum ranges from red to blue, meaning from weak to strong. In other words, stronger light has a higher frequency. The higher the frequency, the bluer the light. Conversely, the lower the frequency, the redder the light. When light becomes so strong that it exceeds the visible spectrum, it turns into ultraviolet rays, or UV rays for short. Beyond UV rays are X-rays, which we use to scan the human body. Even stronger than X-rays are gamma rays, which scientists use to destroy cancer cells. But what about the opposite direction? When light becomes so weak that it can no longer be seen by the naked eye, it turns into infrared or infrared radiation. Weaker than that are microwaves, and finally radio waves. The shift in light is used by astronomers to measure the distance and speed of celestial objects. If a light appears blue and intense, it means it is moving toward us at a terrifying speed. If it appears red and faint, it means the celestial body is moving away from us. In 1912, American astronomer Vesto Slipher discovered a bright spot in the sky with an intriguing characteristic. It was blue, meaning it was approaching us, but the intensity of this blue light showed that it was coming at an incredible speed, up to 3 km/second. At such a tremendous speed and with that kind of light, this object couldn't possibly be within our galaxy. And indeed, it wasn't part of our galaxy, because it was an entirely new galaxy, the Andromeda Galaxy. In the following years, his research revealed that many other galaxies were flying through the universe at astonishing speeds. By 1921, a galaxy named Drea was discovered, and it was moving away from us at a speed of up to 2,000 km/second. There were too many galaxies flying in different directions with different speeds, showing no uniformity. Why could galaxies move like this? If the universe was static, then everything should follow a set orbit, right? Slipher wasn't the first, nor was he the only one, to look up at the sky and accidentally uncover evidence of a dynamic. In 1922, Russian astronomer Alexander Friedmann developed Einstein's equations and proposed that the expansion of the universe was entirely plausible. He even suggested that it was possible to calculate this rate of expansion. Then came American astronomer Edwin Hubble, and the story became clear. Hubble measured the distance between newly discovered galaxies and our own, then compared that to the redshift data of those galaxies from Slipher's research. From that comparison, Hubble revealed the nightmare hidden behind the universe's beautiful facade. Distant galaxies are redshifting faster than those near us. That means the farther an object is, the faster it is moving away. This doesn't mean that we are the center of the universe. Rather, it is the space within the universe that is expanding. Everything is moving away from each other. All matter is separating at an increasing rate. Edwin Hubble quickly published his discovery in 1929, allowing other scientists to witness the true nature of the universe. Among these scientists was Einstein, who recognized the undeniable truth before him. He could no longer continue his research on the cosmological constant. In other words, his static universe collapsed. Einstein's misstep has since become historically renowned, demonstrating that even giants can stumble. However, this mistake did not mean the world turned its back on Einstein. On the contrary, it was a significant advancement for global science. Now we have two core elements shaping our world. First, Einstein's gravity, and second, some mysterious force pushing everything apart. Where there is mystery, there is intellect. Scientists plunged into researching the universe's gaps like moths to a flame. Why is everything moving apart? This question deeply embedded itself in astronomers' minds, compelling them to propose hypotheses about dark energy and dark matter to explain this mysterious phenomenon. However, this is just the beginning. The universe is still too vast and deep to claim that we have uncovered the complete picture of everything. Somewhere out there, questions await us, challenging us on our journey to the origin of all things. And here's a question that perhaps neither Einstein nor Hawking anticipated. Our limited understanding of the universe is what drives humanity to rise and master the skies. This leads to predictions about everything, incomplete laws, and theories not yet reaching the primordial times. Humans name the sky with poetic terms like myths and legends. One such enduring name is the Milky Way, coined to describe the luminous white stream in the sky. Since the concept of a galaxy emerged, astrologers have sought to understand and explore it. Democritus was among the pioneers who ventured beyond this world into the galaxy. To him, the white streaks in the sky were countless stars. But Aristotle had a slightly different story. Around the 4th century BC, Aristotle proposed that the universe originated from divine fire rising from the stars. Of course, we now know this isn't true. At a time when the concepts of cosmology or astronomy had yet to take shape, astrology was all we had. True to its name, astrology means stargazing. Astrologers of that era merely observed stars and recorded their observations for future generations to build upon. In 964, Persian astrologer al-Sufi discovered a massive cloud in the sky and documented it in his book, The Book of Fixed Stars. At that time, he only recognized a dense, bright white stream without knowing what he was seeing. But this record provided future generations with something to study and eventually name Andromeda. In subsequent times, astrologers continuously made predictions about the sky and non-scientific laws to clarify the world. However, lacking scientific evidence, almost none left a lasting mark on humanity. But by 1610 everything changed. Galileo Galilei created the telescope, transforming astrology into astronomy. Up to that point, all predictions about the sky revolved around the idea of a vast sea of stars and clouds. The universe primarily revolved around Earth, and we were the center of everything. However, observations through telescopes gradually proved the opposite. In 1750, Thomas Wright, an English astronomer, published a study titled An Original Theory or New Hypothesis of the Universe, in which he presented his views on the universe. He believed that we live in a galaxy shaped like a flattened disk, containing numerous stars and many clouds. In 1755, building upon Wright's work, the genius Immanuel Kant proposed that those clouds might actually be separate galaxies, which he referred to as island universes. In the following years, brilliant minds and their telescopic lenses continuously gazed at the skies, counting stars to determine the boundaries of the universe, along with a number of clouds, or island universes, that Immanuel Kant had suggested. Eventually, by around 1781, French astronomer Charles Messier identified approximately 103 strange bright spots in the sky, which he believed could be different island galaxies. Although the process of observation and documentation might appear linear, that astronomers observed something, wrote it down, and the world agreed it was true, the reality was not so simple. The tension between the idea of a unified universe and a universe composed of many island galaxies sparked intense debate among scientists. One side believed these clouds were merely clusters within our own galaxy. The other side insisted that they were entirely separate galaxies, not necessarily within the same system as ours, but which side was correct? Born in 1889, Edwin Hubble was a young man blessed with a robust physique and abundant physical strength. With his athletic build, Edwin quickly became a star athlete at school and excelled in sports such as football, baseball, and track and field. However, he gave up all his physical achievements to pursue intellectual ones. When he attended the University of Chicago, Edwin devoted himself to mathematics, philosophy, and especially astronomy. He eventually graduated with a Bachelor of Science degree in 1910. The following years were marked by the bombs and bloodshed of World War I, a time when history was blurred by violence. However, Edwin was fortunate enough to survive and escape the war. After the war, Edwin immersed himself deeper into astronomy and earned an official position at the Carnegie Institution. And this is where everything changed. At that time, Edwin was stationed at the Mount Wilson Observatory, which housed the Hooker telescope, the world's largest telescope at the time. With this new position, Edwin dove into analyzing the photographs taken of the Andromeda cloud, searching for unusual features in his observations. Through this passion, Edwin gradually realized something extraordinary. Within the Andromeda cloud was a Cepheid variable star. Cepheid variable stars are a special type of star that pulsates with a specific cycle and stable luminosity. By observing these stars, we can record their pulsation period, and from that calculate the distance between the star and us. Edwin Hubble recorded the pulsation of the star and the Andromeda cloud and determined the distance from Earth to that star. What was that distance? According to Hubble's estimates, Andromeda is approximately 930,000 light-years away from us. That staggering number immediately shattered all doubts about the cloud within our galaxy theory. Andromeda was not just a cloud, it was far too distant to be within our galaxy. Therefore, it had to be a separate galaxy entirely. And just like that, The debate over whether our galaxy was the only one came to an end. Even though his discovery changed the world, Hubble didn't stop there. He continued his work by studying other galaxies and calculating their distances from us. And then, another shocking discovery emerged. The light from these galaxies was red-shifted, meaning these galaxies were moving away from us. Even more surprising, the farther the galaxies were, the faster they were receding. The expansion of the universe is not constant. It is not uniform. It accelerates over time. This means that, in a distant future, we may no longer be able to see any other galaxies. Space would have expanded so much that all incoming light would exceed the threshold of visible light, and the night sky would be nothing but darkness. This earth-shaking discovery stunned the scientific community. It not only contradicted the static universe model, but it also challenged Einstein's theory of relativity. After extensive verification and independent observations, Hubble's discovery was finally accepted as truth. The universe is expanding at an astonishing rate. However, just how astonishing remains a mystery. In the following years, Edwin Hubble sought to calculate the rate of this expansion, but he was unsuccessful. That elusive number continues to puzzle even today's top scientists. The initial value was estimated at around 500 kilometers per second per megaparsec. However, this number has fluctuated with each new study and context. And so, to this day, the quest for the Hubble constant remains unresolved. Regardless, the fact remains that the universe is expanding, and Hubble's work proved it. Edwin Hubble continued working at the observatory until the final days of his life. He passed away in 1953, leaving behind a monumental legacy regarding Andromeda and the constant that bears his name. However, that constant is not the only thing the world remembers him for. In 1990, the Hubble Space Telescope was launched into Earth's orbit. Ever since, it has shown humanity not only the grandeur of the universe, but also its miracles. In 1995, a lens captured a strange cloud shaped like a hand and named it the Pillars of Creation. 20 years later, thanks to the Hubble telescope, we witnessed the majestic spectacle of a supernova explosion, along with the time-ripping, light-bending shockwave it created. Not only that, but thanks to Hubble, we also learned that the universe is approximately 13 billion years old. Pluto has multiple moons. Every galaxy has a supermassive black hole at its center, and, most intriguingly, the 3D model of what we call dark matter. But that's only half the story. If the universe is expanding, how far does it expand? And the very expansion of the universe has proven that it must have had a beginning, that everything must have once been unimaginably small before it expanded into the vastness we see today. So then, where is the beginning of the universe, and what did it look like? Interestingly, the answer did not come from a scientist, but from a Catholic priest. Why would someone who follows God turn to science? And does the beginning of the universe have anything to do with God? These are the questions we will answer in the next part. Science and religion are two concepts that seem inherently opposed. While one side wants us to look at evidence to explain why something exists, the other wants us to believe in its existence, even without evidence. This contrast is the reason why many brilliant researchers of the past met death before they could witness the results of their own work. However, what is this life, if not a reservoir of wonder? And then the intersection between faith and evidence arrived. At the beginning of the 20th century came a theory to be debated. A theory accompanied by an explosion. Why does this universe exist? This seemingly meaningless question was actually one that many philosophers and scientists were deeply concerned with. They could hardly accept their helplessness in the face of a massive universe that simply existed without any apparent reason. Meanwhile, religions and faiths had their own answers. They claimed that the universe was created by some god, from a supernatural metaphysical force that human beings could never fully comprehend. Though these two opposing ideas never truly clashed directly, the debate between atheism and faith has always existed, like a ticking time bomb, just waiting to explode. Yet while those bonds ticked away, we made a fascinating discovery about the curtain of the cosmos. In the early 1960s, two American physicists, Arnold Penzias and Robert Wilson, were working at Bell Telephone Laboratories in Holmdel, New Jersey. There, they had access to a large radio antenna capable of receiving signals from space. With its highly sensitive radio wave detection, the observatory allowed researchers to peer into the night and uncover its secrets. And in 1965, the two did exactly that. Through their observations, Penzias and Wilson detected a mysterious radio noise. It was extremely faint, but incredibly persistent. It appeared in every observation, every signal, and every experiment, as if it were being broadcast 24/7. At first, they thought this interference came from Earth-based sources, city lights, airplane signals, or even a bird's nest on the antenna. But even after eliminating all possible causes of interference, they still couldn't find the origin of this noise. And that was when they realized the one thing that had always been around them, and they had never suspected, was the universe itself. After comparing notes with prior research, the duo proposed the hypothesis that this noise came from ancient radiation, that it was residual energy from a long-distant past. Why so? Essentially, when energy is released, it leaves behind a trace in space, like how light flashing into our eyes leaves a glare, even after we close them. And just like that glare, it fades over time. But the rate of fading corresponds to the strength of the original energy source. The greater the energy, the longer it takes to fade, and for that energy to still remain today as faint radio noise, it must have come from an unimaginably massive explosion, a terrifying burst of light, strong enough to scorch all matter. Not just burn it, but to excite it into a state. Not gas, not plasma, but something so exotic that modern physics still hesitates to name it. This remnant is called the cosmic microwave background radiation. Researchers began measuring it, trying to determine where it came from and when it originated. After compiling their findings, they concluded that it was the leftover energy from an explosion that occurred approximately 13.8 billion years ago. These details might sound vague and inconclusive, but, in the eyes of researchers, this discovery formed a foundation upon which they could together look back into the past, into a study conducted more than a decade prior, into the origin of everything, into the spark that ignited all existence and left behind the cosmic microwave background, the very thing that Penzias and Wilson stumbled upon in 1965. What was that study? It was the study of the primeval particle. Today we understand that matter is composed of tiny particles called atoms. While this advanced concept has only become mainstream in recent centuries, the idea of particles dates all the way back to ancient Greece. Around the 5th century BCE, the ancient philosopher Democritus proposed a theory about the composition of all things. He believed that everything was made from fundamental particles so small that they could not be divided any further, and he called them atomos, meaning indivisible. This idea was developed further by Democritus and his teacher Lucius into a theory of particle structure. When these particles connected with one another, they formed different configurations, thereby giving rise to different kinds of matter. However, this ahead-of-its-time theory from the ancient philosophers did not receive widespread acceptance, as it was strongly opposed by other thinkers, most notably Aristotle. Aristotle believed that matter was not made of particles, but rather of something continuously changing, without end, and divisible infinitely. That idea eventually evolved into the theory of elements, asserting that all materials in the world were composed of 4 basic elements: fire, air, water, and earth. But the world would eventually change. The particle theory returned, this time championed by brilliant scientists who used it to explain the very fabric of our universe. It paved the way for other great minds to build upon it to explain the origin of all things, and among those great minds was Georges Lemaitre, born in July 1894 in Belgium. Georges Lemaitre grew up in a Catholic family. From an early age, he showed exceptional talent in science and mathematics. That brilliance gradually led Georges to a passion for math and physics. In 1911, he enrolled at the Catholic University of Louvain to study natural sciences. However, before he could complete his studies, World War I broke out and Georges was drafted into the military. His time in the army did not extinguish his passion for science. Instead, it gave him mental space to think about future work. So, upon returning from the battlefield, he immediately went back to university and completed his bachelor's degree. He continued his studies at Cambridge University, where he was directly taught by Arthur Eddington, one of the pioneering scientists behind Einstein's theory of relativity. Surrounded by great minds, Georges pursued his academic path and eventually earned a PhD in physics from MIT. But what made Georges truly special was that he wasn't just a physicist, he was also a priest. During his years in school, he had been ordained by Cardinal Desire Joseph Messier. Thus, Georges became a scientist with faith in God, a uniquely refined combination. In the early 1920s, that refined combination led him to become a professor at Louvain University, where he and other brilliant minds of the time studied Einstein's proposed model of a static universe. During the first decade of observing the universe and the redshift of distant stars, Georges and his colleagues realized that the universe could not be static. It had to be expanding. At the same time, Edwin Hubble was also studying distant stars and beginning to propose the idea of an expanding universe. However, unlike Hubble, Lemaitre delved deeper into Einstein's general relativity and its implications. According to Einstein, the universe operates under gravity, the interaction between massive particles within space-time. But if gravity alone governed these particles, the universe should be contracting, not expanding. Therefore, there had to be some cause behind the expansion. From that, Georges proposed that the universe could not be expanding as it is today without having a starting point, and so he came up with the idea of the primeval atom, or singularity, a point that allowed the entire universe to expand. He called it the primeval atom. Georges published this idea in 1927 in Nature, a scientific journal that was relatively obscure at the time. As a result, virtually no one noticed his theory. But everything was about to change. In 1931, Georges Lemaitre published his idea of an expanding universe, proposing that the cosmos we have today originated from a singular point, extremely dense and unimaginably hot. Not stopping there, Georges further stated that the release of energy from this singularity would lead to a massive explosion, giving rise to cosmic background radiation that we would eventually be able to detect once science matured enough to observe it. In short, Georges was trying to tell the world that this universe was born from a great explosion, one that would scorch space itself and leave behind a lasting stain in the cosmos, a mark we would later discover. His theory caused quite a stir among scientists, partly because many could not believe the universe was actually expanding. For them, Einstein was still right and the universe remained eternally static. On the other hand, they refused to accept that the universe had a starting point, as this notion contradicted the ideals of science. A beginning implied that something or someone initiated creation. Amid this chaotic debate was Einstein's opinion, who claimed that, while Lemaitre's theory sounded plausible, it was in fact utterly nonsensical. However, when Edwin Hubble's research on the expansion of the universe was published, with evidence so irrefutable that no one could deny it, all eyes turned back to Lemaitre's theory of the Great Explosion, and with the prediction of cosmic background radiation being observed in 1965, the world had no grounds left to reject Georges and his work. And so, we arrived at a story of the birth of everything. The expansion of the universe confirms that everything once began smaller and denser. Somewhere in the past, all things were unimaginably tiny and dense, denser than the core of a black hole, and hotter than anything we've ever witnessed. This was a time when nothing yet existed. Time and space had not been born. Everything was contained in a singularity, a minuscule point that held everything, yet did nothing, because there was no space, no time, and thus the laws of physics did not apply. We cannot understand what the universe was or how it functioned at that moment. Then light was born. The Big Bang unleashed all the matter within the singularity, turning the universe into a dense sea of extreme temperatures. The explosion unintentionally created two fundamental concepts: time and space. Time had to exist for anything to proceed, and simultaneously space had to exist for things to occupy. The immense heat of the explosion burned space, leaving a fading stain over time. In the first brief instance of the explosion, matter was released, drastically reducing the density of the universe, giving particles room to move, space to move. As these particles slowed down, the universe cooled. In the next few minutes, nuclear fusion took place, forming light elements such as hydrogen and helium. This cosmic cooling process, over hundreds of thousands of years, allowed for the formation of heavier elements and also allowed light to travel through space, eventually becoming the cosmic microwave background radiation. These heavier elements later interacted with space-time, creating gravity, which pulled in lighter elements, gradually forming massive chunks of matter that gave birth to stars and planets. Meanwhile, the universe kept expanding, stretching the fabric of everything into the future. The story of the formation of all things in the universe, or the Big Bang theory, has answered nearly all questions regarding the existence of physical phenomena in astronomy, while there are still many unanswered aspects, such as the precise equation governing the rate of expansion. The model itself has proven its validity and now serves as a foundation for other great minds to build upon and expand in the future. However, the existence of the Big Bang theory has also made many scientists uneasy, those who study the origin of everything, to deduce laws that explain it all. It is difficult to place faith in something that cannot be proven. True, we are witnessing the consequences of the Big Bang, but physics at the point of origin cannot be explained. This renders all other theories nearly useless. In a way, we are unintentionally affirming the existence of God through the Big Bang theory. Therefore, some argue that this is not the beginning of the universe, it is merely the rebirth of all things. This is the theory known as the Big Bounce, that everything will eventually collapse, and the entire vast universe will become a singularity, followed by another Big Bang in an endless future. With this line of thinking, we don't need to acknowledge the existence of God to explain the presence of modern physics. However, regardless of what we believe, the universe is indeed expanding. The Big Bang remains the most reasonable explanation we currently have. Therefore, the work of the priest named Georges Lemaitre still shines as a bright medal among the achievements of humanity's most brilliant scientists. For his discoveries, Georges Lemaitre has been recorded in the history of cosmic science, alongside Edwin Hubble, as one of the founding fathers of the law on the universe's expansion, known as the Hubble-Lemaitre law. However, being a man of strange humility, George lived the rest of his life as a researcher and lecturer at the University of Louvain, without concern for fame or prestige. He passed away in 1966, 1 year after his prediction about the universe was given solid proof through the discovery of cosmic microwave background radiation. But is the Big Bang the only time we've brushed against the concept of God in the history of science? Could it be that the Big Bang is not the only piece of evidence pointing to the existence of some higher power? That is the question we will seek to answer in the next part. In the 20th century, humanity reached the peak of scientific achievement. Einstein introduced the theory of relativity and changed the entire universe. At the same time, brilliant scientists developed quantum mechanics or quantum field theory to change the entire world. Today, when we look up at the sky, we can use relativity to calculate and predict the movements of stars and planets. On the other hand, when we look at tiny particles, we can use quantum mechanics to calculate and predict the behavior of those particles. That should be enough, right? From the farthest reaches to the tiniest elements, we have the tools to calculate everything, do anything and explore whatever we desire. But things are not that simple. These two extremely solid and standard theories have points of incompatibility. They operate independently, are unrelated to each other, and are applied in different ways. This means that fundamentally, we are using separate theories to explain the same thing. This leads to the idea that these seemingly comprehensive theories are in fact incomplete. For the theory of relativity to be complete, it needs to be able to explain quantum interaction. Conversely, quantum mechanics is only complete if it can explain the interactions between distant stars, in the way Einstein completed Newton's laws of gravity. We are also standing before a new horizon, looking at Einstein's relativity and the quantum mechanics developed by generations of scientists, and having to admit it's not complete. From this, a new mission has been set for the greatest minds on the planet. It's the challenge known as the Holy Grail of science, the unified theory. The purpose of the unified theory is just as its name suggests, to unify relativity and quantum mechanics into a single framework, a single theory, to explain everything and every physical phenomenon from the smallest to the largest. However, this is no easy task. Fundamentally, quantum mechanics and relativity are not alike and are not general. To understand this, we must look back at the atomic model we once studied. Usually we think of an atom as having a nucleus with electrons orbiting around it, resembling a central star with orbiting planets. However, quantum mechanics paints a completely different picture. With deeper analysis using quantum mechanics, we find that the nucleus is not exactly a solid particle, but a group of interacting quarks. There are two special types of quarks, up quarks and down quarks. Their combinations form protons and neutrons. Specifically, two up quarks and one down quark form a proton, while two down quarks and one up quark form a neutron. These quarks are held together by the strong force, mediated by particles called gluons. In essence, the nucleus is not really a solid core, but a tangled cluster of quarks interacting with each other to form a specific energy bundle. The electrons that orbit the nucleus are also not simple particles with defined orbits, like planets around stars. They are energy clouds, certainly influenced by the nucleus and definitely surrounding it. But we don't know exactly where they are. We only know for sure that they are there and that they interact with other energy particles when placed in the right conditions. Therefore, at its core, the structure of an atom resembles a cloud that represents the probability of energy particles appearing. In other words, we don't know the exact orbit of a particle, but we are sure of its presence and specific properties that can be calculated. To know exactly where a particle is, we must define both time and space to specify its location and the moment of its appearance. This is one of many reasons why quantum mechanics separates time and space into two distinct concepts. However, Einstein's theory of relativity treats them as one and sees them as directly affecting our world. Because time and space are one, we can observe time dilation when astronauts travel into space. Moreover, Einstein's formula for gravity allows scientists to accurately predict the positions of planets, stars, and celestial movements down to the minute. Quantum mechanics and relativity are already difficult to reconcile, but it becomes even more complicated because the interactions between quarks are mediated by gluons. So, what about the interaction between planets? What kind of particle would that be? From this question, the hypothetical concept of the graviton was introduced, aiming to turn gravity into a force that can be calculated by quantum mechanics. However, gravity is not really a force. It does not have a direct effect. Instead, it is a consequence that occurs when mass points affect space and time. Therefore, we cannot turn gravity into quantum mechanics. This has led scientists to search for other theories that can encompass both relativity and quantum mechanics, not only explaining the tiny activities of fundamental particles, but also predicting the movements of planets in the sky. To this day, no theory has achieved this. The most prominent among unified theories is string theory, but string theory has not been experimentally verified and remains a theory on paper with countless different equations. This is what we have so far, a collection of incomplete theories about the universe. The greatest minds of humanity are still stuck and have been stuck before the immense work of creation. What we understand is still too small compared to what we do not understand or know, but what we do not understand is itself dwarfed by how much more we do not even know that we do not know. The universe is too vast, too immense, and too complex for one lifetime to witness all the wonders it can create. We still have many questions about the existence of all things and why we are here. Somehow everything is happening as a perfect design that we cannot explain. So then, what are the things we do not know? And what are the things we do not know about how they are? During the development of relativity theory, Einstein encountered an obstacle called the cosmological constant, denoted by the symbol lambda. This was something he introduced to answer the question, why is the universe expanding? Thanks to the research of Hubble and Lemaitre, we know that the universe is expanding because of a big explosion that happened about 13.88 billion years ago. Hence, Einstein's constant was repurposed. Now, instead of explaining why the universe is expanding, this constant is used to measure the influence of dark energy. And intriguingly, when we think about this number, a frightening story emerges. The cosmological constant is calculated to be an extremely small number, nearly zero, but still large enough to impact our universe. However, if this constant were to change, everything would be drastically different. The expansion rate of the universe would slow, gravity would dominate everything, and the distances between stars and planets would be tighter, making conditions for life to exist very difficult. Conversely, if this constant were larger, matter particles could never condense into celestial bodies. So this constant has been finely tuned so that life can exist? Not necessarily, but let us look at some other constants. We live on a special planet, so special that it is hard to find another one like it anywhere in the entire universe. The distance between this planet and the Sun is about 151 million kilometers. The orbit of this planet around the Sun may change over time, but the variation is not enough to significantly alter that 151 million figure. But what would happen if the Earth were not 151 million kilometers from the Sun? If the distance were 155 million kilometers, the temperature would drop sharply, water might freeze, and the life we witness daily would be entirely different. Not only that, our blue planet also has a crust that is both just hard enough and thin enough to allow geological activity, with a thickness between 15 and 20 kilometers. The Earth's crust is rigid enough to control geological activities, so lava and volcano eruptions are not rampant everywhere, while still soft enough to allow tectonic plates to shift, so life can migrate from place to place. Over the Earth's many evolutionary periods, we must also consider that our planet is accompanied by one of the gentlest stars, the Sun. The Sun is neither a large star nor a small star. It lies in the main sequence, meaning it is in a stable active phase and shines just enough. If the Sun was smaller, the energy it radiates would not be enough to warm the Earth, nor would its gravity be sufficient to attract enough material to form surrounding planets. However, if the Sun were larger, it would burn all the surrounding planets and might even form a binary star system. Therefore, the exact diameter of 1.92 million kilometers of the Sun, with a mass about 109 times that of Earth, is necessary for life on Earth to exist. To talk about life on Earth, there are countless other constants that must be finely tuned to an astonishing degree for living organisms to survive. For example, the molecular structure of water, which is considered a necessary condition for life, consists of 2 hydrogen atoms connected to 1 oxygen atom, forming a compound that can exist in 3 states: solid, liquid, and gas, allowing it to adapt to planetary environments. Besides these precise constants, there are other fascinating numbers, such as the gravitational constant g in relativity, which determines the strength of gravity, the electric charge constant E, which governs the strength of electromagnetic force, the masses of fundamental particles like electrons, protons, and neutrons, Max Planck's constant, approximately 6.26 x 10^34 g, which defines the relation between energy and the frequency of electromagnetic radiation, the ratio between strong and weak forces in quantum mechanics, about 100 times, and the list of these constants goes on, many of which provoke more debate than conclusive answers. We cannot avoid these numbers. So what does this mean? Does it mean that this world was created with such meticulous and comprehensive fine-tuning to allow life to emerge? This is when we confront the concept of the Grand Architect. The idea of the Grand Architect is often introduced into debates about the origin of the universe, serving as a substitute for the concept of God. As scientists debating these constants, we can easily find ourselves caught in a loop of thoughts between faith and science because it is just so miraculous, so compelling. We then tend to believe that this universe could only have been created by some master engineer or a great designer. From there, the concept of fine-tuning was brought into scientific discussions as a spark that ignited intense debates. If we believe in fine-tuning, that just a slight deviation or a small change in the constants' values would make life impossible, then we are placing our trust in a grand designer who set these constants precisely so that we could exist. However, if we do not believe in fine-tuning, and consider those constants to be mere coincidences, we have discovered that we are nothing special, then we need a more effective explanation than current theories like relativity and quantum mechanics. Even if we accept that these constants are immutable and that any small change would cause life to vanish, we have no way to prove this claim. Suppose it is true. Do we have evidence to support it? Because we are the only evidence in the entire universe at present that life can exist with these constants. We cannot assert these inferences as facts, because that would be biased. Since we are unique, we are the chosen ones. But as the great astronomer Carl Sagan said, absence of evidence is not evidence of absence. If we place ourselves as the chosen ones, we are excluding all other possibilities of witnessing life forms elsewhere. And this is the crux of the entire debate. In our exploration, we have found some evidence for fine-tuning, but that evidence is not strong enough to completely rule out other possibilities. The universe is too vast for us to truly believe in a fixed list of constants and claim that no other beings like us exist out there. We do not know for sure what lies beyond. This world is too immense for us to think we can answer all the remaining questions. There are too many things we do not know that we do not know. But precisely because of that, we must be steadfast in what we can prove, test, or formulate as laws. The existence of the Big Bang may be evidence of something greater than what we have ever known. The merging of relativity and quantum mechanics might be the answer to the Big Bang. Or perhaps, all of this is just a stepping stone for humanity to advance to a new level of understanding about the universe around us. Whatever the case, science remains science. Knowledge helps us know what is right and what is wrong, but still leaves enough room to acknowledge that in the future we might be wrong and then learn what is truly right. And that was the story about the Big Bang and the foundational debate about the existence of a cosmic designer. We cannot go deeper and more thoroughly into every detail of this debate here, but we hope that through this brief story, you gain a better understanding of the universe around us and what science is striving to prove. If you like the content we have presented here, please share your thoughts in the comments below and let us know what you would like us to add. To support us, you can hit the like button and subscribe. Thank you all for listening.